When you're building a library and it refers to generated code, you want to make sure that you can evolve this generated code in a way that doesn't break your compatibility of the entire library. This is something I've been working on for smithy4s for the last couple of weeks, and I'd like to tell you about what it looks like, how it works, as well as use this opportunity to talk about how you can also contribute to smithy4s and how you can get familiar with the code base, with the code generation process, and we'll talk about that a little bit today as well. So yeah, the feature is called bincompat-friendly mode, or binary compatibility friendly mode, or bincompat-friendly code gen. And it's been a long-awaited feature. We actually would have benefited from having it much sooner because we actually did have a change in the Smithy standard library that kind of caused us to basically let in a breaking change in the generated code. And because smithy4s in its core module also has some generated code, that was essentially breaking compatibility for the library. So we just want to make sure that doesn't happen again for us or for you if you are making smithy4s based libraries, which is not that uncommon. When you generate some case classes using smithy4s, based on a structure, you'll get a case class. You just get a case class and that's it. And case classes, if you are not aware of this yet, they are not very easy to evolve in a binary compatibility friendly way. What this means is that when you add a new field, like let's say we have a city state, if we generate that, you'll just get a new field added to the case class, and it's actually making quite a lot of changes to the Java bytecode that the JVM will be using at runtime, because it adds a getter, it adds a parameter to the copy function, to the constructor, to the apply method, to the unapply method's output, and essentially none of these changes are friendly to binary compatibility. So if you were to compile a library against a version that had the previous version of this, there's a very high chance that when you make this change to the library, the application will no longer work. It will just throw no such method exceptions or other linkage errors from the JVM. So we have to avoid that, right? And the idea in smithy4s that we went with is we have this special trait called bincompat-friendly. And when you generate code with this, you have to add it like from the start. You need to have this trait because it completely changes how case classes are or how structures are rendered. As a matter of fact, this is no longer a case class. We just have a normal class, which will kind of simulate or emulate the features of a case class so that from the outside it's kind of still convenient to use. So we have a private constructor. That's the number one thing that we needed to make, so that the constructor doesn't change its shape, and you, as like a public API user, you don't see the shape, the changes, and you are not affected by them in a breaking way. So we hide the constructor. We also do not have the copy method. It's not public. We have a private one. We don't have an apply. We don't have an automatically generated by Scala apply method. We have our own apply method. And note that this says members available since the beginning. We'll get to this in a moment, but for now, this is all the members we have. Name and country, they're both here. We have nothing else. And because this is not a case class, we had to generate an equals, a hash code, and a toString so that it still looks from the outside like a case class. We also don't implement the product interface because, again, like relying on the methods of the product interface might get you in trouble, so we just don't provide that for you. This might change in the future, I don't know, maybe we'll see. And because we do not have a copy method, we instead provide these kind of setters, immutable setters, these with something methods. So we have with name, with country, these internally use a copy method, but that's all you see from the outside, just these two. Now, let's say I want to add a field, right? So when I just do this, add another field, it will actually still have a breaking change. The apply method now has 3 parameters, and that is just not going to work. So instead, when you are adding a field, you actually have to annotate that field as something that has been added. In this case, that's exactly what you do, bincompat added, and this requires a version. This should be just like a numeric version separated by dots, something like 1.0 or 1.00. That's fine. And there are some validations around this, which you can see directly here in the IDE. You must not have a required field added if it doesn't have a default, because it kind of makes sense. Like, you cannot just add something required and expect it to work in the previous versions of data, because like, what value would the user have here? We can use a default value like a empty string, but that's sometimes not what you want to do. Instead, what you can do is just not make it required, just make it optional. And when we generate this, actually, let me go back to the version without the field altogether. When we generate with the field, we have just additions of new methods. Okay, something is wrong here. Of course, I'm missing an import. Yeah, because it was removed when I formatted the code. Now we just got the withState method as a new thing. We got changes to the existing method so that it's included in toString, hashcode, and all that. And the apply method is unchanged. The old one is still the same. This is members available since the beginning. These are members that do not have a version. They are not added. And then we have a new apply method, which actually includes everything up to version 1.0. So we have these 3 members. Now, if I added 2 members right here, like state, let me add just state 2 because I'm lazy. We still have 2 apply methods because the second one will have 4 parameters, first one has 2. What happens when I have another version, like I want to add some more fields? I have to add a new version because just adding to v1 or the default version would break one of these 2 apply methods or both. So I need to add a new one. Let's say version 2.0, state 3, we generate. Now we have 3 apply methods. And now the last one contains everything up to version 2.0. So we have 5 parameters here, all of them. But the previous members remain unchanged. These public methods are also unchanged. And that's basically how we roll here. So this is how the feature works in structures. We also have bincompat-friendly unions and enums and int enums, but I will not get into the details of that. I don't think it's particularly interesting. This is definitely by far the most complicated how we deal with structures. And if you want to learn more about what these other shapes would be rendered as in bincompat-friendly mode, I encourage you to read the docs. I tried very hard to explain the problem and the things that we do to these shapes as we change them for bincompat-friendly mode. There are also references here to the general rules of how to make your library binary compatible in the future, or like safe for evolution in a bincompat-friendly way. All that is linked here. I hope it's useful. Now, let's talk about how I went and implemented this feature. And before we get to that part, I think we need to go through like the general overview of how smithy4s CodeGen works. This is also a work in progress document, a contributing file. By the time you're watching this, maybe it's already been merged. The code generation process has a couple phases, and they are kind of separate classes in the CodeGen module, but also some of these things are kind of interleaved. But more or less, these are the 4 main things that we do when we generate code. First, we need to build up some kind of representation of these Smithy files that you have and all your Smithy dependencies, all the additional jars that you may want to have, the config that you have, like what transformations you want to run during the CodeGen process. And this all happens in this so-called model loader. And that's basically a function from all these files, jars, strings to something we call a model. The model type comes from the Smithy model library, from the official Smithy lang repo. And it's the so-called semantic model of everything that you have in your Smithy files, in your Smithy model. Now, we can do a lot of things with the semantic Smithy model, but it's not exactly built in a way that is very convenient to generate code from, especially for Scala. So before we get to any kind of thinking about what the output generated code will look like, we have to transform this model to something that is more convenient to use to generate Scala code. And this thing is called an intermediate representation, or IR. And it's a data type that we define somewhere in the CodeGen module. It's something that basically contains all the information necessary to generate Scala code without having to further analyze like dependencies between shapes, or which shapes are recursive, which ones need special handling. We basically do all this kind of analysis and transformation in the Smithy to IR phase. So we take the semantic Smithy model and we make all these adjustments and convert it to this IR data type or set of data types. Then we have some further transformation that just takes the IR and returns another IR, the same type, just with some changes such as, some escaping or sanitization of keywords, because you cannot, for example, have a field in your case class which is named case. That is not possible because case is a keyword, so you have to escape it in some way, for example, by adding an underscore or wrapping in ticks. In smithy4s, we currently do underscores. We also do some transformations to avoid you accidentally referring to something else. Like if you're referring to something called list, we want to make sure that this is a Smithy list and not the Scala pre-def imported list. So just trying to avoid these ambiguous references. And finally, after all this transformation, we basically just generate strings from the IR, the strings that will basically be your Scala files and will later be written to some directory on your disk. I know that's a lot to take in at once. Thankfully, we don't have to touch all of these areas today just to add this bincompat-friendly feature, because the most changes are actually in the rendering phase. So just like taking the IR and outputting strings. But before we can even implement these changes so that some shapes have this special handling and some of them do not, we need to have something that tells us whether a shape is bincompat-friendly or it isn't. So that is normally, like in code, this is encoded in this bincompat-friendly trait. And this trait is defined in the smithy4s meta file. This defines the smithy4s meta namespace, which just has all these traits that can affect how code should be generated. These are very language-specific traits, which are very specific to smithy4s, which is why we have them here and not in something like the alloy library, which is where we would put things like customizations of how unions can be encoded in JSON. So this is different. This is just traits that affect the rendering, but for example, they will not affect the shape of serialized Smithy shapes. So like JSON parsing, validation, or serialization is completely detached from this, and these things are only for what the code is supposed to look like, not how it's supposed to behave in the kind of abstract Smithy sense. So we have the bincompat-friendly trait, and there's a bunch of validations here. I will not go through all of these. These are kind of limitations that we have today, like you cannot use bincompat-friendly mode on errors or inputs and outputs of operations, like direct inputs and outputs. But you can use this for like members of an input or members of an output or of an error. That's fine. That's absolutely fine. A few more limitations in how you can use this with the ADT trait, which is also in this meta namespace. But in many cases, you'll still be able to use bincompat-friendly mode to make your library safer. And in the future, we might be able to get rid of these limitations as well. So we start with this trait definition. We specify which shapes it can be applied on and which traits it conflicts with. This is how you define a trait. You actually use a trait to define a trait. I find it very interesting and confusing. I cannot navigate here in Z because it still doesn't have that feature, but I can navigate here. This is why I didn't use VS Code. It doesn't know how to highlight this. But yeah, trait is a trait, and trait is a trait, and it's a very recursive definition. And yet it somehow works. So we define this trait. We also define this bincompat added trait in the same namespace. And there are also validations here. For example, it must be used in a structure that's also bincompat friendly and nothing else. Like, we don't support this in unions. We don't support this anywhere else. It can only be on members, direct members of a bincompat friendly trait. This is using the selector syntax from Smithy. We will have a video about this sometime. I think I talked about this briefly in one of the Smithy CLI video, I think. That's a nice, convenient way to write these validations, for example, without having to write Java code, which is the usual way that you would write a validator. But it can be a little difficult to decipher, which is why you still need to test this, why you still need to kind of know what you're doing and apply all the usual practices like verifying with manual tests and automatic tests, of course. So now that we have the trait, we need to have some kind of way to check in the code generation process if a shape has that trait. And there are essentially two ways that you can do this. You can check by supplying the fully qualified name of this trait, like as a string, like I'll just write it here, but this would be in Scala, in the Scala code gen. Something like shape has trait, smithy4s meta, bincompat friendly. That's exactly it. You could do it this way, but if we were to have any kind of fields inside, then you would need to basically kind of dynamically inspect the content of the trait. Like in the case of bincompat added, we would have to extract this version field, make sure it's a string, make sure it's present, and all that is normally encapsulated in a kind of strongly typed Java representation of this trait. So instead of has trait, you can do, instead of has trait with a string or a shape ID, you can do shape has trait, and you can specify a class. For example, class of like bincompat friendly trait. That's the usual convention. But the problem is someone has to write this class. Like, someone has to write that code. Thankfully, we now have a code generation process for this, and it's part of the Smithy standard repositories. This is not something we implemented in Smithy4s. Yeah, you can just generate these typed definitions of your traits from Smithy code to Java, which is great because it now will work in all the IDEs, like in the LSP and in the command line as well. This also includes things like deserialization. So given a node, which is like kind of like a JSON AST, it's a representation of this, like how you apply this trait. This is the node. So given this, you can decode to a convenient representation, which will become more apparent in bincompat added because it actually has a version field, which is a string, and it's set, using this. We can actually decode the node. It will take care of this for us. So now that we have this typed representation, we actually need to make one small change to the intermediate representation, or to the process of creating it. The way that we check if something has a trait or not in the renderer is we need to first have this in the IR, in the intermediate representation. So this is encoded, like traits are encoded as hints. We have hints in like the runtime variant of Smithy4s. Like if you go to, we have hints. This is again a representation of traits, but in the code gen process we also have like I would say simplistic or simplified version of the same thing. It's just called a hint. You'll find it in Smithy4s code gen internals. And it's a sealed trait actually, instead of just, like an open world of all the traits. This encapsulates only the traits that we're interested in for the purpose of generating code. So what you'll mostly find here is things from the smithy4s meta namespace. So I added bincompat friendly and bincompat added. We also have our own version number type for the version. We needed our own version number type, and it needs to have some kind of structure so that we can compare these versions, because we actually sort them. We sort them when we generate these apply methods so that they're kind of incrementing. So these are the rules that this ordering follows. We have tests for this. If you find any bugs, please report them. And yeah, we sort at some point. So I added these two hints. or types of hints. And in the smithy2ir process, we actually create them. We have this nice trait to hint function, which takes a trait and returns a hint, but it's a partial function. We only keep some of those. We also have a shape here. I don't think it's actually being used for anything. I'll just remove that at some point. So we check if the trait that we're looking at is an instance of bincompat-friendly trait, because Smithy will actually kind of discover these Java classes on your class path. And if it finds a class like this that corresponds to your Smithy trait, it will actually use this class and create an instance of it. In the case of bincompat-friendly, is kind of just like a marker. You just say that it's there and you don't have any fields, so we just convert to a case object. But bincompat-added trait has fields. We have to extract them and parse the version number, and then we have this bincompat-added class. That's all for this section. Now we can move to the renderer. And in the renderer, the biggest changes are in here in render product non-mixin. So we render a product type or a case class. Well, now no longer just case classes, but just products which are not mixins. If these were mixins, we would go into a completely different code path and generate a trait instead of a class. So that's why it says that. In the product type, we have a convenient isBincompat-friendly method, which just looks at the hints. If it has bincompat-friendly, that's what it will consider it. So we actually use this in 5 places apparently. And basically everywhere that there's a difference in how the normal rendering would work and bincompat-friendly rendering would work, we just have to look at this flag and kind of dispatch to the right implementation. So it starts right here in the first line, actually, because instead of a case class, we have a class with a private constructor, and we have to make some changes to how we generate the parameters of the primary constructor, because normally we would also include like default parameters, and there will be no val prefix. So I actually had to make some changes to allow these modifiers to be added here in the render args function. Another difference is we do not render the serializable super type if it's bincompat-friendly mode. And then we have a bunch of small and kind of inconspicuous looking things, which are just like one-liners apparently, but these actually do most of the heavy lifting. So we have bincompat class members and bincompat companion members. These are things that we will put as methods into the class and the companion object respectively. And this is the biggest chunk of the work in implementing all this. Last but not least, there is like a small difference here in how we implement the make function, but it's not super interesting. It's just like we add the new keyword instead of calling the apply method, we call the constructor directly. But yeah, most of the heavy lifting is in here in render bincompat members and companion members. So in bincompat members, we have to generate, first of all, a copy method. And if you were to write a copy method on all these things by hand, it would be a lot of tedious work. But here in this code, it's a lot of kind of interesting and abstract code, because you do not know how many fields you'll be dealing with, what their names will be, and you have to figure out when to render like the possibly present default value of a parameter. So this hasn't been like trivial, but with just some like testing, trial and error, we got there, and this is it. So the copy method actually has default values in its parameters, just like a normal copy method would in case classes, except when the case class has just one field. Because apparently when it has just one field, every call to the copy method provides all the parameters. So there's no need for a default, and Scala will actually give you a warning. And we want to avoid warnings if possible in generated code. So that's how we kind of disable it. And the implementation is kind of boring when you look at the generated code, because it's just a call to the constructor with all the names of the parameters. I think rendering the parameter list is actually far more interesting, but again, that's just render args, which already existed. So we render the names and the types of these fields and possibly a default value, which actually has to refer to this case class. So that's why we see this default value, this, and then the field name of that field. So we have a copy, but we also need an equals, a hash code, a toString, and the hash code one is the most interesting. It kind of has to recursively put things inside each other. So like here, we fold on the list of fields, starting with some base, which just does a hash of basically the name of the case class, of the structure. So we have to do a fold starting with that, but then the accumulator, the thing that we kind of build up as part of our fold, we just put it more deeply into the expression. So you'll notice that, let's say we have just one field in our fold, you'll see, this is the result. We have the name here, and then we have, well, the name of the class, and then we have the name field. But if I add more of these fields and generate this again with the right imports, we'll see that, name is very, very deeply nested in this whole computation, and instead the latest field is on the outside, on the outermost thing. And I guess that makes sense in some way. I'll admit I didn't think of this myself. I just copied the behavior from Contraband, which is another code generator, which operates on something closer in syntax to GraphQL. It's used a lot by SBT and like SBT plugins. I recommend you check it out, actually. It can be very useful in contexts where smithy4s doesn't make that much sense. But actually a lot of this behavior of this bincompat-friendly mode has been inspired by Contraband, so thanks to the authors for doing all that before us. So that's hash code. Equals, I think, is more straightforward because it's just like there is no need to fold. You just handle each field separately, and then you kind of combine all that with an and that's your implementation. And toString is also quite similar to that. You just kind of render string literals kind of interleaved with references to fields, so that in the outcome you get something like this. And last but not least, we also generate the with something methods, and that is again quite straightforward. We just have with prefix and then some references to the field name and field type, and we call the copy method just because it's the most convenient way to implement this. And these were the bincompat members of the class. We also have bincompat members of the companion, and this is basically just one thing, the apply methods. And I already kind of explained how we produce them, but just again to kind of reiterate, we take a list of the fields and we do like a group by version. These two have no version at all, so that's none. These two have version 1, so that's a sum with 1. And this one has a sum with 2. Then we sort that so that in the situation like, let's say we have something like this, these two, the v1s, are still connected. So we sort that, we end up with something like this, and then we kind of fold on the list, or like scan. I think it's actually a scan. So we start with just these unversioned fields. Then the next version of the apply method will have all these, and then the next one will have all these, and so on and so on. Each one of them gets a comment as well. We just say which members are included in this apply method, so that when you actually call that method, you will see kind of which variant you're calling. There's one interesting thing here in the apply methods. The baseline apply method is allowed to have default values. And what this means is, for example, let's say one of these was optional, then let's look at the first apply. You'll see that the country actually has a non-default value. If I were to have it required with like Poland, if I generate, it will still have a default value, but you'll notice that this default doesn't appear in any of the other methods. And the reason for this is if you have overloads of a method in Scala, only one of them can take default parameters, because otherwise it's just too ambiguous and the compiler cannot tell which method you're trying to call if you are relying on these default parameters. And I think it's actually an error at this point, like it doesn't even compile if you try to compile that. So it's not, you don't even have to call this method, it's just not allowed in the first place. So you're not even allowed to compile such code. And the reason why we even have any defaults in the first place is we still want to make it kind of convenient to construct these baseline versions of your data types, because the baseline version, this one that we've had since the beginning, that's the only one that is allowed to have like required fields, because everything else, the added members, need to have either, they need to be optional or have a default. Then like it just makes sense. Like calling the baseline constructor or baseline apply is kind of equivalent to calling like a normal non-bincompat-friendly case class apply with all these defaults in that signature, if that makes sense. So that's how the feature is implemented. Now, there's still a lot to do beyond that, because we actually have to test this feature and test that it works correctly. And there are basically two mechanisms of testing in here. The first one is just kind of making sure that the code compiles in bincompat-friendly mode. And for this, we use these so-called bootstrapped files. So we have these sample specs in smithy4s, and then we have, oh my god, here, we have these examples. So we just have some kind of shapes that we want to generate code for, and we want to include that in the build process of smithy4s itself. So these are kind of like test input files, and the output of the test is basically like generated sources. So when we compile or like generate something in smithy4s, we'll see these show up as files. Actually, yeah, like this. So that's the representation of bincompat struct after generating. And you'll notice that these files are actually tracked by Git, and we actually do track all the changes to them. So when you make a change to the codegen process, it will also be reflected in how it affects these bootstrapped sample specs. So if I were to say change the formatting of case classes, it would be reflected in all these generated case classes in this module. And you'll see that in the Git diff for the given pull request immediately. If you do not check these files in, it will just fail in the build process, in continuous integration. So you should be doing this. You should be committing these changes. But this only tells us that the code compiled. It doesn't tell us if it's actually, bincompat friendly. So what I did is I also added some kind of integration tests. And I will not get into the very details of how they work, like what they test for, but the general rule of thumb is we generate a bunch of versions of the same kind of structure as it evolves. We start with like 2 fields, then we add a default maybe to one of them, then we add another field and some more, and so on and so on. And we have some Scala code that is referring to the generated code for this. And then basically the implementation makes sure that you can compile the Scala code against the generated code of each of these versions, or like against a library generated from each of these versions. And then it tries to run that code with a different version at runtime of the generated code. And it basically does like, if you compiled your application against generated code v1, then it will work with v1, v2, v3, v4, and so on. If you compile it against v2, it will work with 2, 3, 4, and so on. We do not check against earlier versions. That would not make any sense. They would definitely blow up because some things will be missing. There's some more complicated tests like this where we have like multiple rounds of code generation. This is done to verify that you can still use bincompat-friendly mode in traits. So your traits in your Smithy models can also be bincompat-friendly. And that's really important because the major use case for bincompat-friendly mode is things like smithy4s core itself, which has generated code, which is mostly traits from the Smithy API namespace. So we needed to make sure that you can actually apply these things and they will still compile and they will still run against more recent versions of that source code. So yeah, that's how it's tested. The way that it works, that it actually does the compilation and running all that, we actually use Scala CLI as a sub-process. I think it's a very convenient way to do this. We also, instead of just compiling and running, we also run Mima, the Mima library, on these jars of the generated code alone. But that's kind of like a static analysis kind of test, and you should still be running Mima on your own builds if you're building a library. But that's not sufficient for us to kind of verify everything works correctly. So we also do these kind of full integration tests where we run some Scala code against these different versions of these jars. And in some cases, like when we have actually multiple rounds of code generation for this like trait usage, you will see that we, for example, have like 10 different versions of the application being compiled. And because of all the combinations of like 3 inputs, like 3 evolving versions of a library, all the combinations of this and running that, using that, there's like 57 things to run. So doing all this by hand would not be feasible. So just manually testing this would be insufficient. So that's why we have this. I actually tested with 4 versions. Like this is the number we get with 3, 57. With 4 versions, it's actually over 200 things to run. Yeah, that's quite a lot of things that we test in a single run of this integration spec. It takes a bit of time. I do not know about the first run, but when you just like run it iteratively, it can take like a minute to run the whole thing. So it's definitely not something you want to do on every compile. But yeah, it's very useful. It has not caught any potential problems yet because they have been fixed before I wrote these tests. But when I did disable bincompat-friendly mode, or I deliberately made a bug in the logic of rendering, it successfully found these incompatibilities. So I think it's a very, very useful thing to have. All right, so this is it. I hope this deep dive into the CodeGen process and this new feature has been useful. If you liked it, let me know. If you would like to contribute to smithy4s, if you want to find something that's easy to get started with, also let me know. Join our Discord and ask questions whenever you want to, and we will try to help you help us. So yeah, thanks for watching, and I'll see you in the next video.